Atmospheric circulation and weather systems. In the earlier essay, we had seen how uneven distribution of temperature over the surface of the earth takes place. Air expands when heated and gets compressed when cooled. This results in variations in the atmospheric pressure. The result is that it causes the movement of air from high pressure to low pressure, setting the air in motion. Air in horizontal motion is wind. Atmospheric pressure also determines when the air will rise or sink. The wind redistributes the heat and moisture across the planet, thereby maintaining a constant temperature for the planet as a whole. The vertical rising of moist air cools it down to form the clouds and bring precipitation. This essay explains the causes of pressure differences, the forces that control the atmospheric circulation, the turbulent pattern of wind, the formation of air masses, how air masses interact with each other, and the phenomenon of violent tropical storms. Atmospheric pressure. The weight of I column of air contained in a unit area from the mean sea level to the top of the atmosphere is called the atmospheric pressure. The atmospheric pressure is expressed in units of millibar. At sea level, the average atmospheric pressure is around 1000 millibars. Due to gravity, the air at the surface is denser and hence has higher pressure. Air pressure is measured with the help of a mercury barometer or the aneroid barometer. The pressure decreases with height. At any elevation, it varies from place to place, and its variation is the primary cause of air motion, that is wind, which moves from high pressure areas to low pressure areas. Vertical variation of pressure. In the lower atmosphere, the pressure decreases rapidly with height. The decrease amounts to about 1 millibar for each 10 millibar increase in elevation. It does not always decrease at the same rate. The vertical pressure gradient force is much larger than that of the horizontal pressure gradient, but it is generally balanced by a nearly equal but opposite gravitational force. Hence, we do not experience strong upward winds. Horizontal distribution of pressure. Small differences in pressure are highly significant in terms of the wind direction and velocity. Horizontal distribution of pressure is studied by drawing isobars at constant levels. Isobars are lines connecting places having equal pressure. In order to eliminate the effect of altitude on pressure, it is measured at any station after being reduced to sea level for purposes of comparison. The low pressure system is enclosed by one or more isobars with the lowest pressure in the center. High pressure system is also enclosed by one or more isobars with the highest pressure in the center. Now let us take a look at the world distribution of sea level pressure. The world distribution of sea level pressure in January and July is as follows. Near the equator, the sea level pressure is low and the area is known as equatorial low. Along 30 degrees north and 30 degrees south are found the high pressure areas known as the subtropical highs. Further polewards, along 60 degrees north and 60 degrees south, the low pressure belts are termed as the subpolar lows. Near the poles, the pressure is high and it is known as the polar high. These pressure belts are not permanent in nature. They oscillate with the apparent movement of the sun. In the northern hemisphere, in winter, they move southwards and in summer, northwards. Forces affecting the velocity and direction of wind. As we know, air is set in motion due to the differences in atmospheric pressure. The air in motion is called wind. The wind blows from high pressure to low pressure. The wind at the surface experiences friction. In addition, rotation of the earth also affects the wind movement. The force exerted by the rotation of the earth is known as the Coriolis force. Thus, the horizontal winds near the earth's surface respond to the combined effect of three forces: the pressure gradient force, the frictional force, and the Coriolis force. In addition, the gravitational force acts downward. Let us see how these forces affect the nature of the wind. Pressure gradient force. The differences in atmospheric pressure produces a force. The rate of change of pressure with respect to the distance is the pressure gradient. The pressure gradient or the speed of wind is strong where the isobars are close to each other and is weak where the isobars are apart. Frictional force. It affects the speed of the wind. It is greatest at the surface, and its influence generally extends up to an elevation of 1 to 3 kilometers. Over the sea surface, the friction is minimal. Hence, wind flows with very high speeds. Coriolis force. The rotation of the earth about its axis affects the direction of the wind. This force is called the Coriolis force after the French physicist. It deflects the wind to the right direction in the northern hemisphere and to the left in the southern hemisphere. The deflection is more when the wind velocity is high. The Coriolis force is directly proportional to the angle of latitude. It is maximum at the poles and is absent at the equator. The Coriolis force acts perpendicular to the pressure gradient force. The pressure gradient force is perpendicular to an isobar. The higher the pressure gradient force, the more is the velocity of the wind and the larger is the deflection in the direction of the wind. As a result of these two forces operating perpendicular to each other, in the low pressure areas the wind blows around it. At the equator, the Coriolis force is zero and the wind blows perpendicular to the isobars. The low pressure gets filled instead of getting intensified. That is why the velocity and direction of the wind are the net result of the wind generating forces. The winds in the upper atmosphere, that is 2 to 3 kilometers above the surface, are free from frictional effect of the surface and are controlled mainly by the pressure gradient and the Coriolis force. When isobars are straight and when there is no friction, the pressure gradient force is balanced by the Coriolis force and the resultant wind blows parallel to the isobar. This wind is known as the geostrophic wind. The wind circulation around a low is called cyclonic circulation. Around a high, it is called anticyclonic circulation. The direction of winds around such systems changes according to their location in different hemispheres. The wind circulation at the Earth's surface, around low and high on many occasions, is closely related to the wind circulation at higher level. Generally, over low pressure areas, the air will converge and rise. Over high pressure areas, the air will subside from above and diverge at the surface. Apart from convergence, some eddies, convection currents, orographic uplift and uplift along fronts cause the rising of air, which is essential for the formation of clouds and precipitation. General circulation of the atmosphere. The pattern of planetary winds largely depends on 1. Latitudinal variation of atmospheric heating, 2. Emergence of pressure belts, 3. The migration of belts following the apparent path of the sun, 4. The distribution of continents and oceans, and 5. The rotation of the earth. The pattern of the movement of the planetary winds is called the general circulation of the atmosphere. The general circulation of the atmosphere also sets in motion the ocean water circulation, which influences the Earth's climate. The air at the intertropical convergence zone, that is ITCZ, rises because of convection caused by high insolation and a low pressure is created. The winds from the tropics converge at this low pressure zone. The converged air rises along the convective cell. It reaches the top of the troposphere up to an altitude of 14 kilometers and moves towards the poles. This causes accumulation of the air at about 30 degrees north and 30 degrees south. Part of the accumulated air sinks to the ground and forms a subtropical high. Another reason for sinking is the cooling of air when it reaches 30 degrees north and south latitudes. Down below, near the land surface, the air flows towards the equator as the easter lies. The easter lies from either side of the equator converge in the intertropical convergence zone. Such circulations from the surface upwards and vice versa are called cells. Such a cell in the tropics is called the Hadley cell. In the middle latitudes, the circulation of sinking cold air that comes from the poles and the rising warm air that blows from the subtropical high. At the surface, these winds are called westerlies, and the cell is known as the Ferrel cell. At polar latitudes, the cold dense air subsides near the poles and blows towards middle latitudes as the polar easter lies. This cell is called the polar cell. These three cells set the pattern for the general circulation of the atmosphere. The transfer of heat energy from lower latitudes to higher latitudes maintains the general circulation. The general circulation of the atmosphere also affects the oceans. The large-scale winds of the atmosphere initiate large and slow-moving currents of the ocean. Oceans in turn provide input of energy and water vapor into the air. These interactions take place rather slowly over a large part of the ocean. General atmospheric circulation and its effects on the oceans. Warming and cooling of the Pacific Ocean is most important in terms of general atmospheric circulation. The warm water of the Central Pacific Ocean slowly drifts towards South American coasts and replaces the cool Peruvian current. Such an appearance of warm water off the coast of Peru is known as the El Nino. The El Nino event is closely associated with the pressure changes in the Central Pacific and Australia. This change in pressure condition over the Pacific is known as the Southern Oscillation. The combined phenomenon of Southern Oscillation and El Nino is known as ENSO. In the years when the ENSO is strong, large-scale variations in weather occur all over the world. The arid west of South America receives heavy rainfall. Drought occurs in Australia and sometimes in India, and floods occur in China. This phenomenon is closely monitored and is used for long-range forecasting in major parts of the world. Seasonal wind. The pattern of wind circulation is modified in different seasons due to the shifting of regions of maximum heating, pressure, and wind belts. The most pronounced effect of such a shift is noticed in the monsoons, especially over Southeast Asia. The other local deviations from the general circulation systems are as follows. 1. Local winds. Differences in the heating and cooling of Earth's surfaces and the cycles, those developed daily or annually, can create several common local or regional winds. Land and sea breezes. As explained earlier, the land and sea absorb and transfer heat differently. During the day, the land heats up faster and becomes warmer than the sea. Therefore, over the land the air rises, giving rise to a low pressure area, whereas the sea is relatively cool and the pressure over sea is relatively high. Thus, pressure gradient from sea to land is created and the wind blows from the sea to the land as the sea breeze. In the night, the reversal of condition takes place. The land loses heat faster and is cooler than the sea. The pressure gradient is from the land to the sea and hence land breeze results. Mountain and valley winds. In the mountainous regions during the day, the slopes get heated up and air moves upslope, and to fill the resulting gap, the air from the valley blows up the valley. This wind is known as the valley breeze. During the night, the slopes get cooled and the dense air descends into the valley as the mountain wind. The cool air of the high plateaus and ice fields draining into the valley is called katabatic wind. Another type of warm wind occurs on the leeward side of the mountain ranges. The moisture in these winds while crossing the mountain ranges condense and precipitate. When it descends down the leeward side of the slope, the dry air gets warmed up by adiabatic process. This dry air may melt the snow in a short time. Air masses. When the air remains over a homogeneous area for a sufficiently longer time, it acquires the characteristics of the area. The homogeneous regions can be the vast ocean surface or vast plains. The air with the distinctive characteristics in terms of temperature and humidity is called an air mass. It is defined as a large body of air having little horizontal variations in temperature and moisture. The homogeneous surfaces over which air masses form are called the source regions. The air masses are classified according to the source regions. There are 5 major source regions. These are warm tropical and subtropical oceans, the subtropical hot deserts, the relatively cold high latitude oceans, the very cold snow-covered continents in high latitudes, permanently ice-covered continents in the Arctic and Antarctica. Accordingly, following types of air masses are recognized. 1. Maritime tropical, 2. Continental tropical, 3. Maritime polar, and 4. Continental polar or continental Arctic. Tropical air masses are warm and polar air masses are cold. Fronts. When two different air masses meet, the boundary zone between them is called a front. The process of formation of the fronts is known as frontogenesis. There are 4 types of fronts. 1. Cold, 2. Warm, 3. Stationary, and 4th, occluded. When the front remains stationary, it is called a stationary front. When the cold air moves towards the warm air masses, its contact zone is called the cold front. Whereas if the warm air mass moves towards the cold air mass, the contact zone is a warm front. If an air mass is fully lifted above the land surface, it is called the occluded front. The fronts occur in middle latitudes and are characterized by steep gradient in temperature and pressure. They bring abrupt changes in temperature and cause the air to rise to form clouds and cause precipitation. Extratropical cyclones. The systems developing in the mid and high latitude beyond the tropics are called the middle latitude or extratropical cyclones. The passage of front causes abrupt changes in the weather conditions over the area in the middle and high latitudes. Extratropical cyclones form along the polar front. Initially, the front is stationary. In the northern hemisphere, warm air blows from the south and cold air from the north of the front. When the pressure drops along the front, the warm air moves northwards and the cold air moves towards south, setting in motion an anti-clockwise cyclonic circulation. The cyclonic circulation leads to a well-developed extratropical cyclone with a warm front and a cold front. There are pockets of warm air or warm sector wedged between the forward and the rare cold air or cold sector. The warm air glides over the cold air and a sequence of clouds appear over the sky ahead of the warm front and cause precipitation. The cold front approaches the warm air from behind and pushes the warm air up. As a result, cumulus clouds develop along the cold front. The cold front moves faster than the warm front, ultimately overtaking the warm front. The warm air is completely lifted up and the front is occluded and the cyclone dissipates. The processes of wind circulation both at the surface and above are closely interlinked. The extratropical cyclone differs from the tropical cyclone in a number of ways. The extratropical cyclones have a clear frontal system, which is not present in the tropical cyclones. They cover a large area and can originate over the land and sea, whereas the tropical cyclones originate only over the seas and on reaching the land they dissipate. The extratropical cyclone affects a much larger area as compared to the tropical cyclone. The wind velocity in a tropical cyclone is much higher and it is more destructive. The extratropical cyclones move from west to east, but tropical cyclones move from the east to the west. Tropical cyclones. Tropical cyclones are violent storms that originate over oceans and tropical areas and move over to the coastal areas, bringing about large-scale destruction caused by violent winds, very heavy rainfall, and storm surges. This is one of the most devastating natural calamities. They are known as cyclones in the Indian Ocean, hurricanes in the Atlantic, typhoons in the Western Pacific and South China Sea, and willy willies in Western Australia. Tropical cyclones originate and intensify over warm tropical oceans. The conditions favorable for the formation and intensification of tropical storms are 1. Large sea surface with temperature higher than 27 degrees centigrade. 2. Presence of the Coriolis force. 3. Small variations in the vertical wind speed. 4. A pre-existing weak low pressure area or low level cyclonic circulation. And 5. upper divergence above the sea level system. The energy that intensifies the storm comes from the condensation process in the towering cumulonimbus clouds surrounding the center of the storm. With the continuous supply of moisture from the sea, the storm is further strengthened. On reaching the land, the moisture supply is cut off and the storm dissipates. The place where a tropical cyclone crosses the coast is called the landfall of the cyclone. The cyclones which cross 20 degrees north latitude generally recurve and they are more destructive. A mature tropical cyclone is characterized by the strong spirally circulating wind around the center called the eye. The diameter of the circulating system can vary between 150 and 250 kilometers. The eye is a region of calm with subsiding air. Around the eye is the eye wall, where there is a strong spiraling ascent of air to greater height reaching the tropopause. The wind reaches maximum velocity in this region, reaching as high as 250 km per hour. Torrential rain occurs here. From the eye wall, rain bands may radiate, and trains of cumulus and cumulonimbus clouds may drift into the outer region. The diameter of the storm over the Bay of Bengal, the Arabian Sea, and Indian Ocean is between 600 to 1200 kilometers. The system moves slowly, about 300 to 500 kilometers per day. The cyclone creates storm surges and they inundate the coastal lowlands. The storm peters out on the land. Thunderstorms and tornadoes. Other severe local storms are the thunderstorms and tornadoes. They are of short duration, occurring over a small area, but are violent. Thunderstorms are caused by intense convection on moist, hot days. A thunderstorm is a well-grown cumulonimbus cloud producing thunder and lightning. When the clouds extend to heights where sub-zero temperature prevails, hails are formed and they come down as hailstorm. If there is insufficient moisture, a thunderstorm can generate dust storms. A thunderstorm is characterized by intense updraft of rising warm air, which causes the clouds to grow bigger and rise to greater heights. This causes precipitation. Later, downdraft brings down to earth the cool air and the rain. From severe thunderstorms, sometimes spiraling wind descends like a trunk of an elephant with great force, with very low pressure at the center, causing massive destruction on its way. Such a phenomenon is called a tornado. Tornadoes generally occur in middle latitudes. The tornado over the sea is called waterspouts. These violent storms are the manifestation of the atmosphere's adjustments to varying energy distribution. The potential and heat energies are converted into kinetic energy in these storms, and the restless atmosphere again returns to its stable state.